Shin-Ichi Oguni from the Ehime University. He will give us today's Global Non-Community Geometry Seminar talk. Title is Coarse Cartan-Hadamard Theorem with application to the Crossbound Conjunction. Let's welcome.
Thank you very much. So yeah, thank you very much for inviting me here. So okay, so I want to talk about so coarse Cartan-Hadamard theorem with application to the Crossbound conjecture. So this is based on a joint work with Tomohiro Fukaya. So a paper with the same title is published in Journal of Topology and Analysis very recently. So you can, if you are interested in this theme, so I'm happy if you read our paper. So okay. So this is today's plan. Okay. So first, I want to explain. I want to show you main theorem and related topics. So maybe in the section 1, so this is an introduction. So I will skip some details of some properties or definitions. So we prepare some notations in the section 2 and section 3, and finally I will give a sketch of proof. Okay, this is my plan. Okay. So section 1, so main theorem and related topics. So first, let's recall the classical Cartan-Hadamard theorem. Okay, so let Y be an Hadamard manifold, so that is a connected, simply connected, non-positively curved, completely Riemannian manifold. For example, you can imagine Euclidean spaces and the classical hyperbolic spaces, HN. Okay, they are typical examples of such spaces. Okay. Okay. So then, so the Cartan-Hadamard theorem claims the following. So the exponential map from the tangent space at a base point O to the original Hadamard manifold Y is a dihomorphism. So this is this claim is a Cartan-Hadamard theorem. Okay. So I want to consider so it's a coarse version. So if you are interested in coarse geometry, then so your question is okay. But if you are not interested in coarse geometry, then so it's this question is why do you consider this question? But okay, anyway, I want to consider this question. So later you can see some applications of the Cartan coarse version of the Cartan theorem. So okay, so anyway, we will consider this question. Okay. So then, so if we okay, so yeah, so there are some previous results. Okay, we want to introduce two theorems. First one is this. This theorem is shown by John Law in his book in 1996. Okay, so yeah, here is a classical Cartan-Hadamard theorem. This is a coarse version of the Cartan-Hadamard theorem. So let Y be an Hadamard manifold. This is the same setting in the classical Cartan-Hadamard theorem. So then, John Lowe showed a modified version of exponential map is a coarse homotopy equivalence. Okay. So in the classical Cartan-Hadamard theorem, the exponential map is a dihomorphism, and in the theorem by Lowe, John Lowe, he claims that he got a coarse homotopy equivalence between the tangent space and the original Hadamard manifold Y. Okay. Okay, so the following is another theorem, another coarse version of the Cartan-Hadamard theorem. So let's consider a geodesic hyperbolic space Y. This is a kind of coarsely negatively curved space. Okay. So this is a not manifold. So first we need to consider what is a tangent space. Okay. So Higgson law used the open cone over the ideal boundary of the hyperbolic space Y. Okay. So and they constructed a modified exponential map from the open cone to the Y. So, and they showed this map gave this map is a coarse homotopy equivalence between them. Okay, so now we have two theorems, two coarse versions of the Cartan-Hadamard theorem. But so I think this is best coarse version. I don't think so. These are best coarse version because so in the Lowe's theorem, so why he supposed that Y is a Hadamard manifold. So this is not coarse invariant. And also, so Higgson Lowe's theorem suppose that Y is negatively curved. But so I think original Cartan-Hadamard theorem tolerate non-positively curved spaces. Okay, so I want to generalize this theorem, and I want to get best coarse version of the Cartan-Hadamard theorem. So then I need, so how about coarsely non-positive curved spaces? Okay. But what is a coarse non-positive curved space? So this is a problem. Okay. Okay. So now this is our main theorem by Fukaya and me. Okay, so first we introduced coarse convex spaces. So feature coarsely non-positive curved spaces. Okay, so and studied basic properties. And after that, we showed this theorem. So this is I think this is a nice coarse version of the Cartan-Hadamard theorem. Okay, so let Y be a proper coarsely convex space. This is a kind of coarsely non-positively curved spaces, and yeah, this is a coarse invariant property. Okay, so then we have we constructed a boundary. We constructed an ideal boundary of this space, and we constructed a modified version of exponential map. So then, so we showed this exponential, the modified exponential map from the open cone over the boundary to the y is a coarse homotopy equivalence. Okay, this is our main theorem. Okay, so by the way, y is a coarse version. Why is coarse version interesting? So I think so one of the reasons is an application to the Baum-Kohn conjecture. So we recall what is the Baum-Kohn conjecture. Okay. So the coarse Baum-Kohn conjecture claims that so for a nice proper metric space y, so the coarse assembly map mu dot y from the coarse K homology of y to the K theory of lower algebra of y is an isomorphism. So this is the coarse Baum-Kohn conjecture. Okay, so I think yes. So this conjecture is one of most important problems in the coarse geometry. So, and also, yeah, okay. So, so there are many researches around the coarse Baum-Kohn conjecture. So in particular, so Boolean-Use gave some sufficient conditions, and yeah, so indeed, so embeddability into Hilbert space and the property A and finite asymptotic dimension. So these guys are sufficient conditions for the coarse Baum-Kohn conjecture. So I think there are some other conditions, but today I want to skip others. Okay, so I think so. I want to explain one more sufficient condition. This. So I think this condition is not famous, but anyway. So but this so a coarse version of Cartan-Hadamard theorem is also a sufficient condition for the coarse Baum-Kohn conjecture. Okay, indeed. So okay, so Higson Law U the paper in 1993 studied coarse Meyer-Beatrice exact sequence of K theory of lower algebra. Okay, their argument teaches so this homomorphism, the coarse assembly map also coarse assembly map preserves the coarse Meyer-Beatrice exact sequence. So by using this fact, we can show that this coarse assembly map is coarse homotopy invariant. Okay. So and also Higson law showed the open cone over any compact metric space satisfies the coarse Baum-Kohn conjecture. In other words, the coarse assembly map is an isomorphism for the open cone. Okay, so now, so we can understand this theorem is a sufficient condition for the coarse Baum-Kohn conjecture. Okay, so we have a corollary. So our theorem and this sufficient condition imply the corollary. So, okay, proper coarse convex spaces satisfy the Crossbound Conjunction. Okay, this is the corollary. Okay, so by the way, so okay, so yeah, so I don't explain what is coarse convex spaces, but these spaces have many examples, many interesting examples. So this is a question: what were examples of coarse convex spaces? Okay, here is coarse convex. Okay, so we have many metric spaces and finite genetic groups satisfies coarse convexity. Indeed, actually, so Gromov hyperbolic spaces and groups are coarsely convex. And also, so Boltzmann non-positive curve spaces. So later I will give a definition of these spaces. Okay, anyway, so Boltzmann non-positive curve spaces, for example, cat-zero spaces or Hadamard manifolds satisfy the coarse convexity. Okay, and so locally finite historic complexes with natural metrics are also coarsely convex. This implication is their result. Okay, in particular, so Artin groups of almost large type are historic groups, so they satisfy coarsely convex, and so yeah, okay. So so there is another class of groups, and also recently, so they showed that coarsely hairy spaces are coarsely convex. So in particular, so Artin groups of FC type and hierarchical hyperbolic spaces or groups are coarsely convex. Okay, so anyway, so they are all of them are coarsely convex. So these guys satisfy the Crossbound conjunction. Okay. Okay, so now I want to explain what is a coarsely convex space. Okay, so this is the definition of non-positive curve space in the sense of Boltzmann. Okay, so a metric space Y is Boltzmann non-positive curve if so this space Y satisfies two conditions. First condition is first condition claims that Y is geodesic. So for any two points can be connected by a geodesic. Okay. And second condition is a kind of convexity. So take two geodesic, gamma and gamma prime, and take a number. So this is less than or equal to 1. So then we take a point, so divided A by 1 minus A of gamma, and also we take this point. So then, so this distance, the distance of this point and this point is less than or equal to the combination of distance of endpoints. Okay, the blue line is here, and the green line is here. Okay, so this is a kind of convexity. Okay. Okay, this is the definition of Boltzmann non-positive curved spaces. Okay. So I want a coarse version of non-positive curved spaces. So we can naively define a coarse version. We call a naively coarsely convex space. So this is a very naive definition. Okay. So anyway, so a metric space Y is called naively coarsely convex if so we have two conditions. Okay, so its idea is very simple. I want coarse version of non-positive curved spaces. So we permit some errors. Okay. So first one, original in the original definition of Boltzmann non-positive curved spaces, first condition claims that y is geodesic. So we instead of this part, we assume that y is quasi-geodesic. Y is quasi-geodesic space, lambda k quasi-geodesic space. Okay, so take any 2 points, then we have a lambda k quasi-geodesic gamma. Okay, and the second is okay. We permit some errors in this inequality. Okay. Okay, so this is a very naive definition. Okay, so unfortunately, this definition is not good because so this is not coarsely invariant. So in fact, indeed, so take a Euclidean plane with the standard metric, L2 metric, like this. So then this space is a Boltzmann non-positive curved space, in particular, naively coarsely convex. And so you can easily confirm that Euclidean space with L2 metric and Euclidean plane with L1 metric are coarsely equivalent. But this is not naively coarsely convex because so take two geodesic from 0, to NN like this. This is this is gamma, and this is gamma prime. So these are geodesics from 0 to NN. So then, so endpoints are same. So yeah, here is 0 and here is 0. Okay, but midpoint is very far. Okay, indeed. So two midpoints, distance of two midpoints is equal to n. So if we have no constant c. Okay. So this naive definition is not good. So now I want to, okay, so I will show you a definition of a coarse convex space. So idea is very simple. So, okay, yeah, so idea is very simple. We give up considering all geodesics or all quasi-geodesics. We only consider a family of quasi-geodesics. Okay. So first condition claims that so any 2 points can be connected a lambda k quasi-geodesic belonging to this family L. Okay. Okay. So so we want to skip this condition and this condition because these conditions are a little technical. So okay. So in particular, this condition is okay. So this condition is important if I want to define. We want to define the boundary of this space Y. So because yeah, we need this condition to consider so quasi-geodesic ray approximated by M. Okay. So anyway, today in today's talk, I want to skip more explanation. Okay. And third position is very technical. So indeed, if you use only geodesics, so then this condition is automatically satisfied. So this is a little technical. Okay. Yeah. So yeah, this is an explanation. Third is trivial if you consider geodesics. Okay. We skip this remark. Okay, so now I want to give a very simple example. So recall, so the Euclidean plane with L1 metric is not naively coarsely convex, but this is coarsely convex. In fact, any normed vector space is coarsely convex. So because we can take a nice family of geodesics L like this. So this, okay, so this geodesic is decided by the starting point X and this starting unit vector V and length T. So then we have one geodesic. We can define one geodesic like this. Okay, so this L is defined as the set. Okay, so then you can easily check all conditions. All conditions. So this is an example of coarsely convex space. Okay. Okay, so I want to mention basic properties of coarsely convex spaces. So okay, so first one is coarsely convexity is an invariant, is coarse invariant, and coarsely convexity are closed by direct product. And also we can define a nice compactification. So I mean, so we can construct an inner boundary of Y. So, but we skip the details. Anyway, so we have basic properties like this. Okay, so now I want to prepare some notations for a sketch of proof. Okay. Okay, so yeah. Okay, so let x and y let x, y be proper metric spaces, and take maps f and f1 and f2 from x to y. Then, so f is called coarse if f is proper and f is homologous. Okay. So properness means for every bound subset of Y, its plane image is also bounded in the domain X. And so homologous means homologous means like this. So anyway, so if these guys are geodesic spaces, then so this means large Lipschitz maps. Okay. And two maps are close if so two maps are controlled by a constant Shin. So then we call F1 and F2 are closed. Okay. Okay, so and two metric spaces X and Y are coarsely equivalent if there are two coarse maps from X to Y and from Y to X, such that two maps are mutually inverses up to closeness. Okay, then we call these guys are coarsely equivalent. Okay. Okay. So here are very simple examples. The first example is so every bound set is coarse equivalent to the 1 point. And if you consider a closed Riemann manifold, then the universal cover with the lift and its fundamental group with the word metric, and also the Cayley graph with graph metric are mutually coarse equivalent. Okay. And also, okay, so in the introduction, we considered so what is the coarse version of the Cartan-Hadamard theorem? Then, so for example, if you consider a hyperbolic plane, so then classical Cartan-Hadamard theorem implies the exponential map is a dihomorphism. So maybe a naive coarse version. If you consider a coarse version, so maybe first you consider you can try to replace a dihomorphism with a coarse equivalence, but so unfortunately Euclidean plane and hyperbolic plane are not coarse equivalent, so we have no chance if you consider coarse equivalence. Okay. But anyway, so Euclidean plane and hyperbolic planes are not coarse equivalent. Okay. So and also the exponential map is not coarse. So if we consider some coarse version of the Cartan-Hadamard theorem, then we need to modify the exponential map. Okay. So anyway, so why this exponential map is not coarse? Because so you can easily check. So this map is very, very expansive. On the other hand, the inverse of exponential map, that is logarithm, is a coarse map. Okay, so now, so if we consider a coarse version of the Cartan-Hadamard theorem, we want to a weaker concept than coarse equivalence. Okay, so we want to introduce coarse homotopy equivalence. So this is a definition of coarse homotopy equivalence. So let F1 and F2 are coarse maps from X to Y. So then, so F1 and F2 are coarsely homotopic, denoted by this. So yeah, F1 and F2 are coarsely homotopic if we have two maps, T and H. So T is a bonobus map from X to the non-negative real line, half line. Okay, and H is a coarse map from a subset of X times the half line, such that satisfying this condition. So okay, so we can draw a picture like this. So yeah, so take X. So then, so here is height. Height is defined by this map. Okay. So then, so here is the domain Z. Okay. Okay. So so if you restrict the map H on the bottom, then you can get F1. And if you restrict H on the top, then you can get F2. Okay, so then we call F1 and F2 are coarsely homotopic. Okay. Okay, so X1 now, so we can define X1 and X and Y are coarsely homotopy equivalent. So if we have two coarse maps from X to Y and Y to X, such that two maps are mutually inverses up to coarse homotopy. Okay, this is a definition. So we can easily check this coarse homotopy equivalence is an equivalence relation. Okay, so and also we can easily check so coarse homotopy equivalence is a weaker notion of coarse equivalence. So okay, so example, so okay, so we already mentioned Euclidean plane and hyperbolic planes are not coarse equivalent. However, a coarse version of the Cartan-Hadamard theorem by John Lowe in 1996 claims that these guys are coarsely homotopy equivalent. Okay. Okay, so now I want to a sketch of proof. So recall our theorem. So let Y be a proper coarsely convex space. So this is a kind of coarsely non-positive curve space. Then, so we have a modified exponential map from the open cone over the ideal boundary of Y to the original space Y is a coarse homotopy equivalence. So this is a very sketch of proof, very rough sketch of proof. So let Y be a proper metric spaces. So first, we need to construct a nice metric on the boundary. So yeah, if you consider Gromov hyperbolic space, then so it's a kind of visual metric. So yeah, so for Gromov hyperbolic spaces, there are famous metrics. So it's called visual metrics. But we need to construct such a visual metric on the ideal boundary, and also we need to a modified version of exponential map, exponential tutor. Okay, so if we constructed these, then we need to show these guys are a coarse homotopy equivalence by the exponential map, by the modified exponential map. So in fact, we showed first, the domain is coarsely homotopy equivalent to the image, and the image of the modified exponential map is coarsely homotopy equivalent to the range target, original Y. Okay, this is a rough sketch of proof. So the next slide, from the next slide, we want to explain here and here. Okay. Okay, first we want to try to explain a model of proof over here. Okay. So, okay, so for simplicity, we only consider this example. Okay. This argument is based on John Low's book in 1996. So this is a toy proof of this part. Okay. So, okay, we already mentioned the log is coarse, but the exponential map is not coarse. So because the exponential map is very expansive. So nevertheless, so a rescaled version can be coarse. So this rescaled map, this is a contracting map by defining like this. So then this is a coarse map. So I think so. Yeah, this map is very expansive. So by using this contracting map, we can control this map. Okay, this expansivity, we can control this expansivity. So okay, so anyway, we have this is a coarse map. Okay. Okay, so this is an idea of the proof of this example. Okay, so yes, so then yeah, you can easily so this modified exponential map is a coarse homotopy equivalence. Yes, I want to skip this part. Okay, so next I want to try to explain this part, the proof of this part. Okay. So for simplicity, we want to consider this example. So okay, let Y be a tree with a base point O. So like this. Here is base point, and this has some legs. Okay, this is 3, and and consider a total part from O. So yeah, so more precisely, y prime is defined as this. Okay. So okay. Anyway, so in this picture, so y prime is this real line. Okay. Because so geodesic ray from O, geodesic rays. So yeah, this and this are only geodesic rays from O. So y prime is total part is here. Okay. So then, so this total part is corresponding to this part. So total part is coarse homotopy equivalent to the original y. Okay, so okay, so we want to say some comments about two proofs. The first proof use negatively curvedness, because 3 is clearly negatively curved spaces. 3 is a negatively curved space, so we can use negatively curvedness. So indeed, so in order to construct a map from y to the y prime, we use negatively curvedness. So in fact, actually, the map P is the nearest point projection from y to the total part. Okay, like this. If you take y, then Py is here. And if you take y, then Py is here. Okay. So this is an idea of this is a key idea of this proof. And okay, so next I want to explain the second proof. So because I want to because I want to treat not necessarily negatively curved. I want to treat non-positively curved spaces. So we want to avoid negatively curvedness. In fact, in the second proof, we don't use negative curvedness. We only use non-positively curvedness. Okay. So in the definition of the map P, we used negatively curvedness, but instead of P, we give another map Q from y to y prime. So without using negatively curvedness. So this map is a contracting map. So like this. So this is I want to skip the detail, but so you can imagine. So if you take y, so then qy is maybe like here, and also here is here goes to like here, and so anyway, so all points contracting to the O, but we need to control how to appeal to the O, because we want to the Q must be proper So anyway, we can control. So then we have a coarse map Q. So then we can show other. We can show other some by using some calculation. We can say Q is a coarse homotopy equivalence. Okay, so yeah, here is very details, technical details. So we want to skip. Okay, so anyway, so okay, so I can say, yeah. Okay, now I explained a sketch proof of our main theorem. Okay. Switch time. So okay. So thank you very much. I'll step here.
Okay, you finished the talk?
Yeah.
Okay, thank you very much for a very clear talk. Any questions? Does all this costly convex spaces always have bounded geometry? Is that true?
No.
Not really.
Yeah. So you can easily construct costly convex spaces without bounded geometry. So, for example,
do you have counter examples in this page?
Sorry?
Do you have counter example on this page on the left hand side? This all groups. I don't think so.
Sorry. I don't. So anyway, so for example, so if you if you consider some tree, so maybe okay, like this. So okay, so okay, dividing parts. When this tree has increasing dividing part, then this is not bounded geometry, but this is Gromov hyperbolic, so this is costly convex.
Yes. If we consider a subspace, of a costly convex space, does your result imply the Crossbound conjunction for a subspace?
No, I don't know. Maybe no, because okay. So for example, so if you consider some expander graphs, so then you can construct a hyperbolic. So I mean hyperbolic space. You can construct a hyperbolic space which contains these expanders. So clearly, so this is hyperbolic Gromov hyperbolic space. So maybe without bounded geometry, but anyway, this is Gromov hyperbolic or so coarsely convex. So this hyperbolic space satisfies Crossbound conjecture, but this expander graphs don't satisfy the Crossbound conjecture.
Right.
So this is not coarsely convex. Clearly, yeah. Anyway, this is not coarsely convex.
So a causally convex space can contain a space which is not causally convex.
Sorry.
A subspace of a causally convex space may not be causally convex. Okay.
Not causally convex, not necessarily convex.
Not necessarily causally convex. Okay,
Yeah.
I see. So it's not clear the relation between causally convexity and the cause embedded into Hilbert space. Cause embeddability.
I don't
it's
know.
Not clear. It's not clear.
Not clear.
Okay.
Not clear.
From the audience, do you have any questions? Any more questions? Or comments? Okay. Okay, if in this case, let's thank Oguni, Professor Oguni, for the very nice talk, very clear. Thank you very much.
Thank you very much.
Always. Yeah.
And I just want to make an announcement that next week we will have a talk from Cartan-Hadamard from University of Auckland, and the information will come out soon on the seminar webpage.